Okay, I think it is time to start. We have 45 minutes to talk about the JDK in 2018, what's here and what's next. I'm going to catch you up on what's new in the JDK since JDK 8 came out in 2014. Now, we released JDK 9 last September, JDK 10 today, and JDK 11 will come this September. So we started this year on JDK 9 and we'll finish it on JDK 11. Then 2 more releases in 2019. What you'll see with these releases is not a new lambda-sized feature every 6 months, but rather a steady drip feed of various features of various sizes. One release might have many small features and no big features, while another release might have one big feature and no small features. Some of you might run every release in production after, say, a month of testing. Others may upgrade every year, that is, every other release. Still others may stick to commercially supported releases and upgrade only every 3 years. That's why it makes sense in this presentation to look at the broad sweep of JDK 9, 10, and 11. Before I go any further, I'm going to do another straw poll. Who here is running Java 8 in production? Most hands. 7? Some hands 6? Oh, more hands than 7. That's interesting. Okay. So I'm going to talk about 5. Oh, I should have checked. JDK 9. Anyone running JDK 9 in production? No hands. Okay. So I'm going to talk about 5 things. The Java Platform Module System, the Modular JDK, factory methods for collections, all that is from JDK 9. I'm going to talk about local variable type inference in JDK 10 in more detail than in the keynote. And I'm going to trail a feature that might be in JDK 11. So, the Java Platform Module System. In JDK 9, after many years of effort, we introduced a module system into the Java platform. The module system is a big deal because it enables modular development all the way down. The Java language and the Java virtual machine understand modules very deeply, so that the applications you write and the libraries you consume, and even the JDK itself, can all be developed and tested and packaged and deployed as modules with clear APIs and well-protected internals. Making everyone play by the same modular rules has great benefits for reliability, maintainability, and security. So what is modular development? It's all about reuse. In object-oriented programming, the unit of reuse was traditionally the class. Java has wonderful mechanisms for promoting reuse of a class: inheritance for reusing behavior, interfaces for reusing abstractions, separate compilation, dynamic linking, and access control down to the level of individual fields and methods. And Java has had nested classes since 1997, so it's possible for a single top-level class to encapsulate a vast amount of functionality. But of course, no one tries to cram an entire application into a single class. Any real Java program will consist of multiple classes in multiple packages. Programs are really packages, not classes. And now we see programs with dozens or even hundreds of packages. Once your program is that big, the Java language kind of gives up. There are no abstractions in the language to help you reuse multiple packages or to control sharing between them. The only way to share code between packages is with the public modifier, but then the code is shared with everyone. It's not surprising that package friendship in one form or another has been requested many times over the years. So a package is a great way to organize classes, but most people wish there was a way to organize packages too. Modules let you do that. A module is a set of packages designed for reuse. This is a long overdue building block in the Java language. Modules record the structure of your program so that the packages you want to be reused can be reused, while the packages you don't want to be reused cannot be reused. A program built of modules will be more reliable than a program built from a loose set of packages in jar files that can access each other freely and that share internal APIs which have to be public, with the outside world. In other words, programs are modules. Here's a module that everyone will become familiar with, JavaBase. It's the foundation in Java 9 and above of every Java program, just like JavaLang object is the root of every class. In blue are the packages of JavaBase intended for use by code outside the module. These are its exported packages. In red are the packages internal to JavaBase. They can be used by code inside the module, but not by code outside the module. These are its concealed packages. A module is declared in a new kind of file called modulinfo.java. It gives the name of the module and its exported packages. And so by exporting the JavaLang package, it means that the public classes of JavaLang are accessible from outside JavaBase. A package that is not explicitly exported, such as ComSun crypto provider, is concealed. Its public classes are not accessible outside JavaBase. So this is the first important feature of modules, strong encapsulation. A module isn't just a set of packages, it's a set of exported packages and concealed packages. This means that access control is more powerful in JDK 9 and later than in JDK 8. In JDK 9 and later, you can arrange for public classes to be accessible to everyone, or only to other classes in the same module, or accessible to classes in the same module and a limited set of friend modules. So if you're looking at the public modifier on a class declaration, it no longer means that everyone can access the class. Access depends on whether the class's module exports the class's package. Since JavaBase is a module, let's reuse it with a module of our own. Here's the simplest possible program in a package. The package is com.example hello. Let's declare a module for it at the bottom. There's a modulinfo.java file, and for sake of argument, let's export the com.example hello package with the exports directive. Now, you're probably wondering, amongst many other things, how the hello world module knows that it has a package called com.example hello. After all, nothing in the package, nothing in the say hello class, seems to point to the hello world module. It's up to the tooling to decide during development which module each package belongs to. In practice, your IDE takes care of it. You create a modular Java application, you'll ask the name of the module, then every package you create will be part of that module. If you run javac by hand, bottom right, then javac figures out which module each package is in. That's why modulinfo.java is in the src directory at the same level as the com directory, the root of the package hierarchy. Now, the benefit of relying on tooling is that it's really easy to place an existing package in a module and immediately give that package the benefit of strong encapsulation. We do not want each and every class to have to opt in to strong encapsulation by declaring the module it belongs to. That would invite errors, such as classes in the same package attempting to join different modules. That would be a big no-no. One more thing, the say hello class obviously imports the JavaLang package. I didn't show it before because it's implicit, but that import is in every program you write. Now, usually you don't think about this, but it's worth asking, where is JavaLang imported from? Now, you might say, the answer is obviously JavaBase, because you told me a minute ago that JavaBase exports the JavaLang package. And you're right in this case, but in general, how does the compiler find arbitrary packages that you import? Should it search the file system looking for modules which export the imported packages? What if multiple modules export the imported package? If we intend to reuse the JavaBase module by importing its packages, we should document that fact. Actually, since we're writing a module ourselves, we must document that fact. This is the second important feature of modules, reliable dependencies. A module isn't just a set of packages. It's a set of packages that reuses the packages exported by other modules. So the Hello World module specifies that it reuses the Java base module with a requires directive in its module.info.java. This means that code in the Hello World module can import any of the packages exported by Java base. If code in Hello World tries to import any of the packages concealed by Java base, then even the public classes of those packages are out of bounds. It's like when you try to access a package private class from a different package. The compiler gives you an error, and at runtime you get an illegal access error. It's the same thing here if you were to try to import ComSum crypto provider or touch any of its classes. I'd like to say one more thing about that module.info.java file that declares a Hello World module. It's really important to understand that a module exports packages for reuse, but requires modules. The reason is due to an old software engineering principle. The unit of reuse is the unit of release. The principle is ultimately about separation of concerns. You reuse someone's code, not by copy-pasting it into your own source tree, but by depending in some way on the black box artifact released by someone else. Now, in the Java ecosystem, there's no question that the unit of release is the jar file. That does not change with modules. A jar file simply carries the module.info.class file that was produced from module.info.java alongside ordinary class files. We call this a modular jar. So when someone releases a modular jar for the Hello World module, it's reused by someone else writing requires Hello World in their own module.info.java. The reuser benefits from an explicit coherent API consisting of precisely the exported packages, just the one in this case. The releaser benefits from strong encapsulation of concealed packages. There are none here, but maybe there are, they're not shown, right? So even if there is high coupling inside the Hello World module, there's loose coupling between modules. That's another good software engineering principle. If you want to learn more about the module system and ways to actually do modular developments, then I highly recommend this book, Java 9 Modularity, that came out concurrent with Java 9 last September. Let's turn to the JDK itself. 20 years ago, the Java platform was small, just a few hundred classes, and the organization of JDK 1.0 was not a problem. But every year the platform grew bigger, and now it's tens of thousands of classes. JDK 8 was huge, and worse, it was monolithic. Now in reality, the Java platform is about 25 separate frameworks. The Swing UI framework, crypto, scripting, multiple XML processing frameworks, and so on. There is no reason these separate frameworks have to be tightly coupled in one JDK download. And it's actually an impediment in developing the JDK. The overly tight coupling raises development and testing costs, which turns into slower platform evolution. And the larger the surface area of your platform, the more difficult it is to secure. Plus, it's an impediment, the monolithic JDK, to a lot of users, both those who want to run applications on smaller devices and those who want to run more instances of their applications on large systems. Even if you only wanted a part of the JDK, you had to take all of it. In JDK 9, we took the monolithic JDK and broke it up into a few dozen modules. At the bottom, there's Java Base, which everything depends on, and which depends on nothing itself. We broke out the various frameworks into their own modules, logging, XML, scripting, desktop, which you can require or not require as your needs dictate. Near the top, there's a Java SE module, which has no actual code in it, but just has dependencies. So you can say requires Java SE and be guaranteed to have all the standard modules available. Now, it's worth mentioning that merely finding these module boundaries, which might be obvious in hindsight, was a tremendous engineering effort. You'll find in your own code that decoupling a monolith is much harder than building a loosely coupled system from the beginning. The good news going forward is that the discipline imposed by modules prevents all of us from accidentally recreating a monolith. Now, because the JDK is not a monolith, it's possible to create subsets that suit your needs. Suppose your application in green needs JDBC and the Java Activation API. That means it needs the Java SQL row set module and the Java Activation module in orange. In turn, they need further modules. If the watchword for JDK 8 was functional, then the watchword for JDK 9 was transitive. What matters is the set of modules needed transitively by your application. The indirect dependencies are just as important as the direct dependencies. If anything in orange is missing, your application won't start up. What you can do is create a custom Java runtime containing only the modules that your application needs, either directly or indirectly. You do this with the JLink tool. It generates a Java runtime that looks like the JDK, just smaller. You run your application on this runtime using the Java launcher that is generated for you as part of that runtime, my runtime/bin/java. Now, note that your application does not have to be a module itself. You can specify the modules that it needs with the command line flag to JLink. You'll see I've specified Java SQL row set and Java Activation. Question: how do you know which modules to include in your custom runtime? Answer: the JDEPs tool. It analyzes your class files and jars and figures out which modules they need. Let's go back to the modules of the JDK. It is important to realize that various technologies from Java EE have traditionally been included in the JDK, not just in app servers. In JDK 9 and 10, the list of Java EE modules includes JAX-B, JAX-WS, Java Activation, Common Annotations, and Corba in yellow. In JDK 11, these modules will be gone. And I must emphasize that. Gone. 800,000 lines of code. Gone. To prepare for this outcome, the Java EE modules are disabled by default in JDK 9 and 10. If you run your application on JDK 9 and 10, 9 or 10, and you get a no class def found error or a class not found exception, this is probably the reason these EE modules are disabled by default. Now, there is a command line flag to enable the Java EE modules in 9 and 10, but they're not there in 11. So long term, you need to use standalone versions of the Java EE technologies. You are now wondering where to find standalone versions of the Java EE technologies. We documented your options in great detail. Everything you ever wanted to know about this topic, everything, is documented in JEP 320. This is Java Enhancement Proposal 320. So, let's discuss another aspect of the modular JDK, the strong encapsulation applied to JDK modules. A lot of tools and libraries try to access parts of the JDK that are meant for internal use only. Now, it'll take a while for tool and library developers to move away from this practice. So JDK 9 and 10 allow access to JDK internals temporarily. However, they print a warning when it happens. Now, there's a command line flag to avoid these warnings, but you should check with tool and library developers about how to deploy on JDK 9 and 10. You may also find that tools and libraries fall over because they assume the Java version string begins with 1 dot, 15, 16, 17, 18. And it's not 19, it's 9 dots. Some tools assume that the JDK lives in a file called rt.jar. Some libraries assume that the application class loader is an instance of URL class loader. These are all implementation-specific assumptions that are wrong on JDK 9 and later. So again, please check with tool and library developers about the versions of their tools and libraries that you need to run on 9 and 10. Okay, we'll now get back. Normal service is now resumed. We'll now come back to Java code. There is a question which I'm going to have to take at the end. I'm sorry. Let's look at a new API added in JDK 9, factory methods for collections. Java collections have changed quite a lot over the years. They've added support for new language features such as generics and lambdas. They've gained support for concurrency. And popular classes like ArrayList and HashMap have been rewritten several times for performance. But the core collections API, the list interface, the set interface, the map interface, haven't fundamentally evolved since 1998. So in JDK 9, we added factory methods to list, set, and map. They're convenient, concise, and they return space-efficient implementations. They also promise space and performance improvements from use in the JDK itself. Almost everything is called of. Right? List of, set of, map of, to instantiate an instance of list, set, or map. Now these of methods are declared as static interface methods. Recall that since JDK 8, you can put code in interfaces with default methods and static methods. In JDK 9, you can also have private methods in interfaces to help out, avoid your default methods getting too long. Here are examples of list of and set of. Far less verbosity. Now, an important property of these methods is that they return unmodifiable collections. There's no need to wrap them with collections unmodifiable list or collections unmodifiable set. Being unmodifiable means that any attempt to add, set, or remove elements throws unsupported operation exception. And we think this is a good thing because it means you can pass your private collections to other code without fear of accidental modification. Also, it's often the case that collections which are initialized from known values are never changed. So unmodifiable is a better default than modifiable. And of course, unmodifiability is one step towards immutability and freedom from data races. Map.of also returns an unmodifiable collection, far more readable. By allowing keys and values to be passed in line, it saves even more code than its list and set counterparts. Now, when you have more than 10 entries in a map, all the key value pairs would be a little unreadable if they were passed without any structure for the compiler to check. So you use map.of entries rather than map.of. Map.of entries is a varargs method, but it takes map.entry objects, which you can obtain for map's new entry method. That's another static interface method on map. I already said that the collections that are returned by these factory methods are unmodifiable, but they have other interesting characteristics too. Let's talk about nulls. It is widely believed that allowing nulls in collections back in JDK 1.2 was a mistake, and no collection type introduced in Java 5 or later has allowed nulls. The obvious reason for this belief is that nulls in a collection allow null pointer exceptions to surface everywhere. The less obvious reason is that nulls are useful as sentinel values in APIs, such as map.get and map.compute. They're also useful as sentinel values for optimizing implementations. So when you use the factory methods, nulls are not allowed as list members, set members, map keys, or map values. If you pass a null to a factory method, it'll throw null pointer exception and fail to create the collection. let's talk about duplicates. When you pass values to a factory method, it's probably a mistake if you have duplicate set elements or duplicate map keys. Now, ideally, this will be detected at compile time, but the values you pass to set.of and map.of don't have to be compile time constants. So the next best thing is for the factory method to fail fast at runtime by throwing a legal argument exception. Finally, let's talk about the iteration order for set elements and map keys. Now, for hash sets, for the hash set and hash map implementations, the order of iteration is officially unspecified. However, it's usually consistent for long periods of time and over multiple JDK releases. And unfortunately, that means order dependencies can inadvertently creep into code, and then lots of code breaks when the JDK changes the iteration order for performance or security reasons. So, the collection implementations returned by set.of and map.of make the iteration order predictably unpredictable. It'll be stable within a running JVM, but will change from one JVM run to the next. The goal is to toughen up user code to prevent inadvertent dependencies and have bugs flushed out in development rather than production. This is all a long-winded way of saying call sorts. Now, to be clear, all of this only applies to the collection implementations returned by the factory methods. No existing code depends on their iteration order. For pre-existing implementations, like hash sets, the iteration order is the same as before. If you really want a specified predictable iteration order, use linked hash set and linked hash map explicitly. Little break. So at last we come to a JDK 10 feature. Under 20 minutes left, that's fine. Local variable type inference. Were you all in the keynote? Let's look at where we use type inference today, pre-JDK 10. Generic methods, parameterized classes, and parameters of lambda expressions. In most, if not all of these cases, removing the type information makes the code easier to understand, not harder, because the original code was already redundant. You can see calling a generic method, you don't need to supply a type argument. With the diamond operator in Java 7, you don't need to supply the type argument to new. With the lambda expression, you can omit the parameter type of a lambda formal. Also, omitting type information isn't just about avoiding redundancy. In Java 8, type inference can handle generic method calls that are nested and chained. This is the secret sauce that makes APIs such as streams so easy to use. The call chaining just works. No one is bothered that the intermediate types from stream and filter, so stream block and int stream, and the type of the lambda parameter b don't appear in source code. Those types are relatively minor details. Now, it wouldn't be redundant to split up this call chain with intermediate variables of type stream block and int stream, but it would certainly add clutter. So, given that past uses of type inference have been winners, it seemed reasonable to consider new contexts for type inference. We were looking to avoid redundancy, minimize clutter, and allow minor details to be de-emphasized. That's why JDK 10 introduces type inference for local variables with the var keyword. Var tells the compiler to infer the type of the variable on the left-hand side based on the type of the expression on the right-hand side. This is static typing without the ceremony. It's not dynamic typing. The type of string list and stream are both known at compile time, and they do not change after they're declared. As I mentioned in the keynote, this is one of the most frequently requested features from developers coming to Java from other languages. Scala, C# and C++ have this. Java is late to the party because we like to look at how well features work in other curly brace languages first. What we saw for local variable type inference is that once you've got used to it, it's hard to live without. C# developers make this point very forcefully when they come to Java. Now, I said that var is a keyword, but technically it's not. It's a special kind of type known to the compiler. So you can still use var in method names, field names, even local variable names if you want. You just can't use var as a type name anymore. var works with all kinds of local variable. That includes the loop variable of a for statement and a resource variable in a try with resources statement. In all cases, there must be an initializer on the right-hand side in order to use var on the left-hand side. It's not good enough to assign the local variable on the next line, because that is a slippery slope to action at a distance where an assignment is made far from the declaration. Now, that's not the end of the world, but it certainly trips up someone reading the code. An even worse kind of action at a distance would be multiple assignments to the name variable. Someone reading name equals Bob might think the type is inferred to be string, but suppose there's a later assignment to name, this time involving a regular expression pattern. Now, you probably do not code like this, but maybe you know someone who does. Someone who thinks it's important to reuse local variables. Now, if the compiler, you might say, why can't the compiler just find both assignments to name? These are local variables, so it's all in the same method body. And why can't the compiler just compute the least upper bound of string and pattern? That would be you might think, oh, great, so that would be object, and so the type of the name variable would be object. Wouldn't be great, but maybe it would be okay. However, what the compiler would actually infer for the type of name is this: string and pattern and comparable and serializable. That is a real type in the Java language. It's an intersection type, but it's almost useless in the real world. By the way, multiple assignments to a local variable also mean it's not effectively final, so it cannot be used in a lambda expression. The bottom line here is that action at a distance with local variables is a bad idea. Declare local variables where you need them and initialize them immediately. Don't delay their initialization and don't reuse them. That then makes type inference work smoothly if you want to use var, and it gives you more flexibility if you want to capture the variable in a lambda expression, and it makes the method body more readable all round. Okay, so we're going to write the initializer immediately. A few more things to be aware of. First, the initializer cannot be null, because that would let var infer any class or interface type at all, and that would be useless. Second, the initializer can't be a lambda expression or an array initializer. They both need an explicit type on the left-hand side in order to infer their own type, which they then use to validate the body of the lambda expression or the values in the array initializer. In addition, you're probably wondering if you can use a diamond operator in the initializer. You can, but the type inferred won't be very good. Let me leave it at that. Speaking of the inferred type, you might be wondering if var will infer a more precise type than you would write yourself. What I mean is, string list will be inferred here as an array list, whereas you might choose to declare it yourself as a list. Generally, yes, it's better to program to interfaces like list than to classes like ArrayList. After all, if the class adds public methods beyond those in the interface, and the public methods are really implementation details, then your code using var could become addicted to them. Now that's a problem, but it's more the fault of new than of var. If a library makes its classes widely accessible and doesn't provide any mechanism for instantiating them, so that everyone uses new, then the library deserves blame for adding arbitrary public methods to its classes. On the other hand, if a library conceals its classes and makes objects available via, let's say, factory methods that return interfaces, then no one will use new, and var will infer an interface. Now, this connects up to something we said before. Bear in mind that public was historically the only way for a class to grant access to its friends in related packages. That's why a class might be stuffed full of public methods to help its friends, rather than to implement a popular interface. But with modules, library owners have a new technique for controlling access. Public classes can be placed in packages that are exported only to friend modules, while interfaces can be placed in packages exported to everyone. There is then no chance of the classes leaking through to client code, and it means that var can infer interfaces from the factory methods, such as list.of, in the exported interfaces. Now, as I said earlier, some people freak out at the loss of type information with var. But tell me, which is more important when reading this code? The type of a local variable or its name? Often it's the name, because that's what you need to see flowing through the method body. The type of the local variable is often just an implementation detail that gets in the way of seeing the flow, and the name usually encodes some information about the type anyway, hence my conveniently chosen example. If you choose reasonable names, the resulting code is often more readable with var than with explicit types. You avoid repetition between the type and the name, and the brevity of var increases the prominence of the name. These factors are why var is only for local variables where the use of the variable is close to its declaration. var is not for fields, and it never will be. Fields are API elements used by code some distance away from the field declaration. The benefit of explicit typing for fields is obvious. The Java doc for a class wouldn't be much help if it said var for all the fields. You'd have to look at the actual field declarations to figure out the type inferred from the initializer. And reading someone else's initializer is no fun. And if it changes, then the inferred type changes too. This kind of instability has no place in an API, so var is not allowed for fields. The same logic explains why var cannot be used as the return type of a method. It would make the return type dependent on the actual return statements in the method body. Nor can var be used in the formal parameters of a method. A method has no idea who calls it, so there's no way to infer its parameter types. One final thing about var. It says nothing about mutability. You have the choice of making the variable final or not. In reality, local variables usually do not need to be final. They are immune to data races. They are the least important place that we need immutability. The only reason, pretty much, that anyone thinks of a local variable being final is because they want to capture it in an anonymous class. But since JDK 8, that scenario is insignificant because lambda expressions can capture effectively final local variables where you don't type final anymore. So if you are wondering whether final var can be spelled val in the interests of encouraging immutability, the answer is no. Where we need help with immutability is fields, but that is a whole other feature for a whole other JDK. If you want to read more about var, I recommend Java Enhancement Proposal 286. If you scroll through it and read it very carefully, to be fair, you'll find a link to an email from Brian Getz where he discusses the design of this feature. And the interesting thing to realize about this email is that it's from December 2016. Brian is discussing in this email 2 surveys that we ran to gather feedback on var, where literally thousands of people responded. You can still read the comments at SurveyMonkey. And we started discussing var even earlier. JEP 286 was created in March 2016. This shows that even if we're shipping the JDK every 6 months, the features that you get in a release have taken much longer than 6 months to come to fruition. You are not getting more features than if we ship the JDK every 2 years, but you are getting greater predictability. When we say a feature is going to be in, we're pretty sure it's going to be in. Let's wrap up in 4 minutes and 40 seconds with a small fun feature that stands a good chance, let me put it that way, of being in JDK 11, raw string literals. As you know, traditional string literals are quite limited. If you want a multi-line string, you usually concatenate a bunch of string literals together with plus. If you want double quote or backslash characters in your strings, you have to escape them. And if your string contains logically delimiters, then you might need a painful combination of escaping and concatenation. With this SQL statement, we got lucky because the only delimiters it's using internally are backticks and single quote characters. But if it had double quote characters in it, we'd need to escape them. Raw string literals are much more powerful. You can spread a raw string literal over multiple lines. It's delimited with backticks, so you do not have to escape double quote or backslash characters. And if your string contains backticks, no problem. You just change the delimiters of the raw string literal to have more backticks than the string itself. You do not change the string in any way. Think about that. You can put anything in a raw string literal, even Java code that contains raw string literals, and you never need to escape it. The only escape syntax occurs outside of the string, at the boundaries, so you can read the string forgetting that it's in a container. There's a bunch of new methods to help process the multi-line strings that are now easier to write with raw string literals. For example, there is trim indent to remove space in the left margin. There's trim markers to remove known markers at either edge. And there's also lines. These are all new methods on string. There's lines, which returns a stream of substrings extracted from the string, partitioned by line terminators. As you can see, it works on strings derived from traditional string literals that escape the line terminator with \n, as well as strings derived from raw string literals. So, what's here is JDK 10, and what's next is JDK 11. I invite you to download JDK 10. You can get it from get binaries from OpenJDK. You can read about local variable type inference in depth. JDK 11 early access binaries are available too. We have, like I say, already removed the Java EE and Corba modules, and we are working hard on prototyping a range of language features. I talked about raw string literals, also maybe switch expressions, search for JEPs 325 and 326 to read more about that. And with that, thank you very much. We have 1 minute for questions. There was a lady here with a question earlier. The question is, if you say var name equals Bob, can you later on say name equals 4? No. The type is inferred based on the initializer. So it's exactly as if you say var name equals Bob, it's like saying string name equals Bob. If you later on assign a non-string to name, it's a compile time error. It's all compile time. It's a very good question. This is all static typing. There is nothing dynamic. var is morally a shorter version of what you would write yourself, notwithstanding the comments I made earlier about interfaces and implementations. Any other questions? One more. Got 7 seconds each. In the cap. question is, Nashorn is Oracle's modern implementation of ECMAScript. It is, actually it's 2 modules in JDK 9. I believe it's still there in JDK 10. So nothing has changed as far as Nashorn goes. Yep. One more question over there. Your application code almost certainly is Java 9 and 10 safe. I very much doubt you are using Sunmisk unsafe defined class. I very much doubt you are hacking via reflection into ComSun crypto provider, like people on Stack Overflow post questions about doing. The libraries that you use, pretty much all of them, do that kind of thing. And I cannot say to you that they will run on JDK 9. I wish I could. You will probably need to upgrade your Spring, your JUnit, your Hibernate, your Maven, your Eclipse, and so on to versions that are 9 aware. They may or may, this is not to do with modules. They may or may not be modularized. They may or may not have support for your application being modularized. That's a much longer effort. But just to run on 9 and avoid those errors, you will probably need, that's why I say check with the tool and library developers for which versions are 9 ready. And most of the big libraries and frameworks are now. I think that is all we have time for because it's yep, we're over time. Thank you.